Our next topic we're going to focus on is discussed in Chapter 15 of your textbook, and that topic is thermodynamics. Thermodynamics is an attempt to answer several questions that we can ask about the universe. The first one is, how do substances absorb and release heat? The second question it tries to answer is, how do chemical reactions absorb and release heat? And the third question is, what makes a chemical reaction likely to occur? The hint, it has something to do with heat. So all these three topics are topics we're going to get to in the next couple weeks. The goal of this video, though, is just to get you used to a few of the terms that we're going to use throughout this chapter. So the first set of terms we're going to focus on are temperature, thermal energy, and heat. Now, these may all sound like the exact same thing, but they're actually subtly different, so we need to differentiate between them. So temperature is a measure of the average kinetic energy of molecules. So if you can imagine a substance, so this looks like a gas, and all of the little molecules are bouncing around. The arrows kind of represent their kinetic energy, so the bigger the arrow, the more the kinetic energy. And they're kind of bouncing around in all the directions. If I take the kinetic energies of all these three molecules, add them together, and divide by 3, I'm going to get something analogous to what the temperature is. So temperature is I take all the different kinetic energies and I divide them by the number of molecules. So of course, we're never actually working with 3 molecules. It's probably going to be more like 3 gazillion. But we have this this average is basically what the temperature is. Thermal energy, on the other hand, is the total kinetic energy of the molecules in a system. So if I go back to this 3-molecule sample of gas, and I take all these kinetic energies and I just add them up, the total number I'm going to get is going to be equal to the thermal energy. So both temperature and thermal energy are expressions of energy. So all of them can be measured in the unit for energy, which is joules, a capital J. Now temperature, as we know, though, is measured not usually in joules, but in degrees Celsius or Kelvin. But you can easily convert between joules and kelvins because temperature basically is kinetic energy. So let's just see if we understand these definitions. So I'm going to ask you a couple questions and answer them to the best of your ability. So if I have a coffee cup at 80 degrees Celsius and a lake at 20 degrees Celsius. So my first question is, which of these liquids, the coffee cup or the lake, has a greater temperature, has a greater average kinetic energy? You should answer the coffee cup, because the coffee cup's at 80 degrees Celsius. That means if you look at all of its molecules, if you zoom in and look at all of its molecules, they are moving faster on average than the molecules in the lake. If you zoomed in on the lake molecules, these arrows would all be shorter than they would be in the cup of coffee. Now my next question is, which has a greater thermal energy, the cup of coffee or the lake? Well, you should answer the lake. Even though the molecules are moving at an average slower speed, there are more molecules, right? So if you just add up all the different kinetic energies of all the molecules, you're going to get a bigger number than adding up the kinetic energies of all the molecules in the cup of coffee. The coffee molecules are moving slower, but there are just more of the lake molecules. So if we are to think about what affects thermal energy depends on both mass and temperature. So the thing with the greater temperature is not necessarily going to have the most thermal energy, because you also have this factor of mass. something with a greater mass is going to have a greater thermal energy, even if the temperature might be lower. And we're going to deal with an equation that relates thermal energy, mass, and temperature later on. But think right now that the thermal energy, it depends on how fast the particles are moving, but also how many particles you have, how much matter is in your sample. So the next definition we're going to deal with is heat. Heat is the transfer of thermal energy from hot to cold. So we talked about the lake having more thermal energy than the cup of coffee. Heat is when you transfer that thermal energy from a hot object to a cold object. So let's look at an example. So if we have an iceberg, and the iceberg is sitting in the middle of the ocean. If the ocean is at 30 degrees Celsius and the iceberg is at negative 20 degrees Celsius, then what's going to happen is the hot water, or the water that is hotter at a higher temperature than the iceberg, is going to transfer its thermal energy to the iceberg. And this is what we call a transfer of heat. Heat is this transfer of thermal energy. So the amount of thermal energy that is transferred from the from the water to the iceberg is what we call the heat transferred from the water to the iceberg. And now the more thermal energy in an object, the more heat it can transfer. So let's look at an example of that. So if you have an iceberg at negative 20 degrees sitting in the middle of an ocean at positive 30 degrees, the ocean is going to start transferring its heat to the iceberg, and potentially, if the water's warm enough and if the iceberg's small enough, that iceberg's going to melt. But let's think about the same deal if you had a cup of coffee. If you walk onto an iceberg and spill a cup of coffee, no matter how hot the cup of coffee is, you're not going to melt the iceberg. There's just not enough thermal energy in the cup of coffee to actually leave a dent in this massive iceberg. So that's why we say the more thermal energy in an object, the more heat it can transfer. The ocean has more thermal energy. Even though it's at a lower temperature, it has more thermal energy than the cup of coffee, and therefore it's able to transfer more heat to the iceberg. So as a result, you can never melt an iceberg using a cup of coffee, but you could potentially melt an iceberg if it sits long enough in a warm ocean. So the next topic we're going to talk about is system, surroundings, and universe. Now, this is a very simple topic. It's deceptively easy, but it is the basis of basically everything else that we're going to discuss this chapter. So it is very important. So the system is basically whatever you want to study, and the surroundings are everything else. Okay, so if you want to study a reaction that's occurring in an Erlenmeyer flask, your system would be the Erlenmeyer flask. If you want to study an ice cube, the system would be the ice cube. The surroundings are going to be the cup of water surrounding the ice cube, the glass in the water, the table on which it sits, the room, basically everything else. So if you add the system and the surroundings together, you get the universe. Okay? So the system is whatever part of the universe you've selected for study, and the surroundings are basically everything that isn't in the system. So pretty simple, right? But let's see if we can apply that to understand what has been termed the first law of thermodynamics. So the first law of thermodynamics says that the total energy of the universe is constant. When God created the heavens and the earth, he also made a fixed amount of energy. And so that energy can be transferred or transformed, but it's never going to change. The total amount of the energy in the universe is always going to be a constant number, a fixed number. Um, this is also known as the law of conservation of energy, but they used it so much in thermodynamics that they also call it the first law of thermodynamics. So if this sounds similar to the law of conservation of energy, it's because it is. Now, given what we said on previous slides, we can also write this law in a different way. If the total energy of the universe is constant, we can also say that heat cannot be transferred to and from the universe. Because if heat were transferred to the universe, then the universe would be gaining energy, right? It would be gaining thermal energy. If heat were lost from the universe, then the universe would be losing thermal energy. So I can write that as an equation. Now, in order to write that as an equation, I have to introduce you to a little bit of new terminology. So whenever I want to write heat in a mathematical equation, the variable that I use for heat is Q. So anytime you see Q in this chapter, it's going to mean heat. And then I put in a subscript whatever that heat is the heat of. So if it's heat transferred to and from an ice cube, it would be Q of an ice cube. And I'd have ice cube in a subscript. In this case, I'm talking about the heat transferred to and from the universe. So I write that as Q and then universe in subscript. So this means the heat transferred to and from the universe. And that's always going to be equal to 0 joules. Joules, again, being the unit of energy. 0 joules. So the heat of the universe, the total heat transferred to and from the universe, is always going to be 0 joules. Now, from the last slide, the heat transferred to the universe can be broken into two parts. The heat transferred to and from the system, and the heat transferred to and from the surroundings. If I can just divide the universe into system and surroundings, I can also divide the universe's heat into system and surroundings. The system being what I'm focused on, the surroundings being everything else. So if that's true, then I can substitute the first equation into the second equation to get that 0 joules is equal to the heat of the system plus the heat of the surroundings. And then doing a little very basic algebra, I end up with this. The heat of the system, the heat transferred to and from the system, is equal to negative the heat transferred to and from the surroundings. So in plain English, what that means is whatever heat is gained by the system is lost by the surroundings. Whatever heat is gained by the surroundings is lost by the system. So let's apply that to a couple examples and see if we can make sense of that in a real world perspective. So if I have a cup of water and I put ice cubes in that water, the ice is ultimately going to melt. Let's say I know that it takes 25 joules to melt all that ice. So then the question becomes, where does that 25 joules come from? Where does that energy come from to melt the ice? Well, the answer is most of it is going to come from this water that the ice is in. A little bit of it might come from the air, but ultimately it's coming from the surroundings. So if I add up all the energy that is lost by the surroundings, both that lost by the water and that lost by the air, I'm going to get that the heat of the surroundings has changed by negative 25 joules. So if it took 25 joules to melt the ice, then I know that my surroundings have lost 25 joules of energy. Let's look at another example. If you have a campfire, right? And that campfire is giving off 25 kilojoules of heat, and the temperature of the area around the campfire is rising, and you can somehow measure that 25 kilojoules of heat are being given off by the fire, that means that the fire is losing 25 kilojoules of heat. And that's mainly coming from the combustion reaction of the firewood. So if the fire is losing 25 kilojoules of heat, then the surroundings are gaining 25 kilojoules of heat. So these two numbers are equal and opposite because we know that Q of system is negative Q of the surroundings. And that guarantees that the law of conservation of energy is being followed. That if you burn a piece of wood and suddenly the room gets warmer, that energy is coming from the fire. It's not just being created. If you see ice melting, the energy it takes to melt the ice is coming from the surroundings, coming from the water, coming from the air. It's not just being created. So I hope that made sense. I hope you have good notes on the 6 terms we've talked about, and then also you have a good understanding of the first law of thermodynamics. We're going to be taking up these topics next class. I will see you then.